Recording. Can you see the whiteboard?
I cannot.
Sure.
Maybe you need to make a screen demonstration.
Yes, I did. Once again.
Oh, yes, it seems working now.
It is working. Okay. Just a second. It is just a little bit too slow. Let's get to the original size. Okay, something like that. Okay. Fokker-Planck partial differential equation. Why it is important? It is by far the most important tool in quantitative analysis of stochastic processes. Why? You remember we mentioned what does it mean actually to solve a stochastic differential equation. It is not the same thing as solving, let's say, an ordinary or partial differential equation. Because if it is stochastic, then the solution is a stochastic process as well. We would never be able to obtain this solution exactly, really, because it is random. Every time you will get a random path of your solution. So it is not the most interesting question of how to represent this path. Sometimes we can do it explicitly. Remember, let's start with a simple geometric Brownian motion. So you remember dst was equal to, let's say it is a constant, mu st dt plus sigma st dwt. Okay, remember that. Then we know how the solution looks like. The solution would be st equals to, you remember, S0 exponent of, it is important that we have a correction for volatility, mu minus sigma squared halved times t plus, this is t, plus sigma wt. But what does it mean? We have a stochastic process here, which is wt, which results in a stochastic process for st. Yes, this exponential solution means that it is positive if S0 is greater than 0 as well. Okay? So that's true. But nothing else actually we can derive from that. It is some kind of function, in this case it is an exponential function of our Brownian motion wt. A much more useful question we can ask is not how to present this closed form solution, but a much more useful question is what is the distribution of st. And for the distribution, straight away, this formula doesn't tell us much. Of course, we know that from this, it follows, or we can obtain it by other means, that log of st divided by s0 is, in this case, mu minus sigma squared halved t plus sigma wt. And because of that, it has a normal distribution, as you remember, normal distribution with the mean precisely being equal to mu minus sigma squared halved times t, and the standard deviation being equal to sigma square root of t. This is already something. So we know that the log of st divided by 0 has a normal distribution, and therefore st itself has a log normal distribution in this particular case. But what about the general case? This is a relatively simple situation, okay? It is a very classical one. You can find it in any standard textbook. It is pretty much clear what we have in this case. But let us consider the general case. In the general case, our one-dimensional SD looks like dst being equal to some function mu, not necessarily a constant, but some function mu of st and t times dt plus some function sigma of st and t times dwt, right? That's the general case. So the question is, can we obtain for this general stochastic differential equation a similar probability density function for our synthetic process? So there is no straightforward answer to this. And that's precisely what the Fokker-Planck partial differential equation will do for us. It allows us to obtain the PDF, the probability density function. What is the probability density function? So first of all, we will denote this probability density function by P. It is a function of two variables, f and t, right? And we would say it is conditioned on the initial value as 0, although we will not write this dependency on as 0 in every case, just to reduce writing. So this P of f and t conditioned on as 0 is what? By itself, it's nothing. But we can say that this P is such that P of f and t conditioned on S0 times ds, and that has a very well-defined meaning. P of st times ds is the probability of our random variable st at time t belonging to the interval from s to s plus ds. That's why it is a probability density function. It's indeed a PDF. It's a probability that st belongs to the interval from s to s plus ds. Therefore,
it's time for a more
at time t, that our stochastic process at times t belongs to the interval from s to s plus ds, where s and t are arguments of our probability density function. Okay? So, I will switch off. Can you see my Telegram? I will switch it off.
Yes, we definitely can see it.
Okay. All, you know, that's all nice. Lots of important messages about biomedical sciences, but unfortunately the subject of our lecture is Fokker-Planck PDE rather than biomedical sciences. Okay, so the question is how to construct this function P of s and t. This function P of s and t is indeed a function which satisfies this Fokker-Planck partial differential equation. Let us, I can write it down for you, but it wouldn't be that interesting. Let us try to derive this partial differential equation. Okay? May I switch to the next screen? Well, you'll get a recording anyway, all right?
Yes, definitely.
Okay. Let us start from a very remote idea. So at the moment we have absolutely no idea of how to construct this differential equation, okay? Our objective is to find this probability density function. Let us do the following. So once again, you remember we have this general form of stochastic differential equation. Let us also introduce some kind of function which I will denote by h of s. Some kind of function. You know, it is going to be a little bit specific function. So what is h of s? Let me introduce it in this way. So this is s, this is h of s. I will do the following. So first of all, this function h of s will be 0 outside the interval AB. Outside AB, this function is 0. Why not? 0 if s does not belong to the interval from AB. Within this interval, the function will be positive. The function will be positive. Just a second. I need to respond. The function will be positive. It will still be equal to 0 at AB. So again, let me say it is 0 when s equals to A or s equals to B. It is positive when s belongs to the interval from A to B. Within this interval, let's say this function is twice continuously differentiable. We'll need this technical property. And let's say, its derivatives at A and B vanish as well. So h prime of A equals to h prime of B equals to 0. Okay? We may also may or may not need to assume that the second derivatives vanish, probably not. Okay? So this function, you see, 0 outside AB, again equal to 0 in A and B, and the derivatives are equal to 0 as well. And otherwise, it is positive inside of the interval AB. Continuous and moreover, twice differentiable in the interval AB. Okay? This type of function. Why not? The second question we would like to do is to consider some time t, and I'm interested in what h of st is going to be. H of st. Once again, ST is our stochastic process, which is given by dst equals to mu of STNT times dt plus sigma of STNT times dWt. Okay, so we're interested in the function s of h of st at some time t. T equal to 0, our initial point. Okay. What can we say about it? We can't say anything, but we can construct a stochastic differential equation for h of st. D of, let's say, dh of st. What is dh of st? We will apply the eta Dublin formula in order to derive this, eta Dublin. We can say that dh of st is, this function only depends on, it doesn't depend on t explicitly. So instead of partial derivatives with respect to s, we can write full derivatives with respect to s, because it depends only on one argument, right?
I'm sorry, but some guys also want to join and they want you to allow them to join.
We may stop people joining when they are late, but for today, I will let this gentleman in if I can.
They are not late, they're trying to connect, but they get the same error at it was in the chat.
Same error. But still, you know, 11 people managed to connect somehow.
Yeah, I don't know how they and why they cannot.
Just a second. Let me double check. We are in. Just a second. The first time we do this, recording. Just a second. I would like to. Okay, I stop sharing screen for a second. Here we are. No, I can't see anyone else. I only have, okay, one more person. Okay, admit.
It seems that at least 3 persons want to join, but they cannot because of they waiting your permission.
I will change the setup next time, so it would be okay to join without permission. For the moment, it was just a default setup. We have 12 people now. I can't see anyone else actually. Okay, let's get back.
Sergey and Zamira want to join. I don't know how and so.
I can't see.
Let's explore a dendrogram.
I can't see anyone else. Unfortunately.
Okay.
We can do, well, in this case, this lecture will be available anyway. And next time, it might be a problem on the client side, it might be a problem on the server side, but now 12 people joined in. I'm absolutely sure about that. let's get again to our screen. Okay. So we're here. Using the eta Dublin formula, we can say what it is actually, dH of ST. This is actually derivative of, I can even say more explicitly, I can say it is just derivative of H a full derivative, not a partial one. Okay. Oh. Sorry. Okay. Of ST times dST plus 1/2 of the second derivative of H with respect to ST. And now you understand why we required our function H to be twice differentiable, right? Because we do have a second derivative here. Times dST squared, which is equal to, let me for sake of brevity just write H prime. You understand it is H prime of ST, H prime times dST. And what is dST? dST is given by our by our stochastic differential equation. Therefore, dST is mu times dt, where again you understand that mu is not a constant, it's a function of ST and t. Okay, mu times dt plus H double prime halved, and dST squared is obviously, you remember we square up this expression for dST, dropping all terms of the order higher than dt, and the only term which is retained in this case is sigma squared times dt. Sorry, I probably did something wrong. Sorry, I didn't finish this. So mu dt plus, apologies, doing this with this type of board is not very easy. H prime mu dt plus, removing this, mu dt plus sigma dwt plus H double prime halved dST squared, which is sigma squared dt. And therefore, altogether we get H prime mu plus H double prime sigma squared halved dt plus sigma dwt. So we got this expression for sigma prime. Therefore, along any path of our stochastic process ST, we can say that by integrating this expression, so we have this dh expression, which equals to this one. Therefore, by integrating it, we can say that h of indeed st minus h of s0 would be equal to a stochastic integral, and we express it as two integrals. First of all, integral from 0 to t. Here, let's write it a little bit more carefully. So what it is going to be, h prime of what? H prime of s with the subscript, I would say su. Mu of s u plus 1/2 h w prime of su sigma squared of su and u du. Okay, plus integral from 0 to t, again sigma of su and u dw du. Now take the expected value of this, apply the expected value operator. Let's see that the expected value of h of st equals to expected value h of st is obviously the initial value, which is a constant, h of s0, plus the expected value of this integral, right? Whereas for the last integral, the expected value is 0, because it is an integral over the Brownian motion, which is independent of our process sigma. Sigma by itself here might be a stochastic process, because SU is stochastic, sigma of SU is stochastic, yes, but dWu is independent of sigma, and therefore it is very easy to see that, we have seen it already on a number of occasions, that the expected value of this integral is equal to 0. Whereas for this integral, we can swap the expected value operator and write it as an integral from 0 to t, expected value of this square bracket h prime mu. Yes.
Sorry, don't we have a little mistake in sigma d omega t should be multiplied by h with differentiation.
Where, in which line?
Third line from the bottom.
Okay.
The last
h prime multiplied by mu dt plus sigma dwt plus
this is fine.
Sigma squared dt equals to, grouping together the terms with dt, h prime mu plus h double prime sigma squared half dt. Oh yes, you are right. You are right. We missed h prime here, right? Yes, h prime. Thank you. Still, it doesn't change anything because the expected value of this is 0. Okay? So, not to worry. H prime mu plus h double prime halved sigma squared. Strictly speaking, du, as we decided. Okay? So that's the expected value of h of st. Okay? But I will clean the screen I will make a copy for myself actually, what I have derived. To go from 0 to t, expected value of h prime mu plus h double prime sigma squared half du. Okay? Okay. Clearing this, we go forward. But on the other hand, why do we expect this expected value of h of st in the first place? We do that because this can also be expressed through our probability density function. You remember that our objective is to find out the value of p of s and t, and therefore we can say that the expected value, suppose that this function is known, the expected value of h of st and t, on the other hand, would be equal to what? It would be equal to the integral. In general, the range of values for s can be arbitrary. That's why I put from minus infinity to plus infinity. H of, this is a dummy variable, so it doesn't really matter. I can say h of s or st, it doesn't really matter. P of s and t, but it is important of that t, ds, correct? And in a similar way, we can construct the expressions for the expected value under the integral. Therefore, what we get? We get integral from minus infinity to plus infinity h of s or st, doesn't matter, p of s and t dt equals to h of s0, as you remember, plus integral from 0 to t, integral from, again, minus infinity to plus infinity, our density, again, p of s and t, multiplied by the expression from which we get the expected value. H prime will then expand this and see what exactly it means. But here it is important that it is actually h prime of su. Mu of SUU. And the density is in the internal point, so it is not ST, it is P of SU, sorry. Mu of SUU plus 1/2 H double prime of SU sigma squared of SUU d SU du. Let us evaluate these horribly looking integrals. There are two of them. Let me denote the first one by I1 and the second one by I2. So I1 is an integral from minus infinity to plus infinity, P of S, let's say SU. Let me write it once again. Integral from minus infinity to plus infinity, P of SU at time U, H prime of SU. We don't even need a bracket here. H prime of SU, mu of SU, U dsu. Any ideas? What should we do with this integral? From your first year mathematical analysis, please, any ideas? Is there anything in the structure of this integral which can help us tackling it? No ideas? You see, there is h prime here. So what does it mean that we have h prime? It means that we can take this integral by parts. You remember taking integral by parts. Therefore, it is going to be h itself of su p mu. I'm not writing the arguments here, you understand. From minus infinity to plus infinity. Minus integral from minus infinity to plus infinity. Now other way around, h by itself, h of su, multiplied by the derivative with respect to su of p times mu dsu. Okay? What can we say about the first term? You remember that our function h is what? It is 0 at both plus infinity and minus infinity, right? It is 0. Whereas the function p and the function mu, we assume to be, we can't assume that mu is bounded at infinity, but we can say that p mu, because p is the probability density which decays at infinity, we can assume that p mu itself is bounded at infinity. Therefore, under some genericity conditions, we can say that this term is 0 at both infinities, right? So this is 0. Therefore, we get minus, just we get only the second integral. So it is just minus integral from minus infinity to plus infinity, h d dsu p mu dsu. Okay? So we only got this term. Now, in a slightly more involved, but still exactly same way, we evaluate the integral I2. I2 equals to, okay, 1/2. Let us carry it along because otherwise we'll very easily forget about it. Integral from minus infinity to plus infinity, h double prime sigma squared dsu. Therefore, taking it by parts once, we get 1/2 h prime sigma squared from minus infinity to plus infinity. Oh, sorry, and obviously there is a p here, and you don't tell me. We missed p. We multiplied by p. Okay? H prime sigma squared p from minus infinity to plus infinity minus 1/2 integral from minus infinity to plus infinity. Now what? We say h prime dsu of sigma squared p dsu. This term outside of the integral is again equal to 0 for the same reason, because h prime is definitely 0 at infinity. You remember our construction of function h. It is equal to 0 along with all its derivatives at infinity, and sigma squared p is supposed to be bounded. Therefore, it is only minus 1/2 of the second integral, but the second integral is again evaluated in the same way using integration by parts. Therefore, it is minus 1/2 now h times sigma squared h times derivative sigma squared p prime from minus infinity to plus infinity. And for the same reason, this term equals to 0, plus 1/2 integral from minus infinity to plus infinity. Now h itself, but second derivative with respect to su squared of sigma squared p dsu. Okay, let us switch Telegram off once again. Okay, therefore, what we got eventually? We got that this term in the left-hand side equals to this term in the right-hand side. Let me probably write it down once again. So we got integral from minus infinity to plus infinity hp dt equals to h of s0 plus integral from 0 to t of these two terms, minus integral from minus infinity to plus infinity h d dsu of p mu dsu plus 1/2 integral from minus infinity to plus infinity h again, second derivative of sigma squared p with respect to su dsu du. That's what we got. Okay, let me take a copy of that. Sorry, one point, sorry, not dt, but obviously ds here. From minus infinity to plus infinity, ds. When we were taking the expected value. Obviously, ds. H of s0 plus integral from 0 to t minus integral h d dsu p mu dsu plus 1/2 integral from minus infinity to plus infinity h second derivative sigma squared p dsu du. Now what we will do, we'll do it other way around. We'll differentiate this expression with respect to t. We'll take a partial derivative with respect to t of this expression. Now you see the left-hand side, it is an integral over s. So when we take a partial derivative with respect to t, we will differentiate inside the integral. Moreover, h doesn't depend on t, and therefore it remains a constant factor in this case. Differentiation is applied only to p. Therefore, let me start the next sheet. What we get in this case, by differentiating with respect to time, we got integral from minus infinity to plus infinity of h of s, partial derivative with respect to t of p only times ds equals to, obviously h of s0, which was there, is has zero derivative with respect to time, it is a constant. And now we had an integral from 0 to t, and that integral from 0 to t, obviously when we differentiate with respect to time, it simply yields the value under the integral. So now we have minus integral from minus infinity to plus infinity, h of, let's say, st, because the value is indeed taken at time t, dst of p of tnt mu of stnt dst plus 1/2 integral from minus infinity to plus infinity, again h of st, second derivative with respect to st, of, again, p of stnt, mu of, oh, sorry, not mu, sigma squared of stnt dst. Now, you see that ds or dst is just a dummy integration variable, which we can denote by any letter, be it s or st, it doesn't matter. So now moving all terms into the left-hand side, we get integral from minus infinity to plus infinity. Let's say we'll denote it by s rather than st. Absolutely doesn't matter. It is a dummy variable. H of s times, first of all, dp dt. Then this term, this integral, is moved into the left-hand side as well with plus dds of p mu minus 1/2 second derivative with respect to s of p sigma squared. Okay? All multiplied by ds identically equal to 0. But now, h of s is an arbitrary function, and the only thing we required from this function is to be sign definite. It is a positive function, right? So h of s itself doesn't vanish. Moreover, now because we know that h of s equals to 0 outside the interval AB. This integral can be replaced by the integral from a to b. Outside this interval, our function h of s equals to 0. Therefore, what is the conclusion? If this equality holds identically for any h of s, absolutely any, only provided that it vanishes outside of AB and it is positive in the interval AB, it can only mean that the integrand itself must be equal to 0 identically. So this term is identically equal to 0. And therefore we get, finally, dp dt plus ddf of p mu of st minus 1/2 second derivative with respect to s squared of p sigma squared of smt must be equal to 0, where p is our function which depends on s and t, conditional on the initial condition as 0. This precisely is the celebrated Fokker-Planck partial differential equation. So basically, what we achieved, starting from an arbitrary stochastic differential equation, you remember with those mu and sigma terms, we managed to derive a partial differential equation which gives us the density, the probability density function of our stochastic process. So now we don't need to construct some artificial strange transforms like one we did for the geometric Brownian motion. Okay, for the geometric Brownian motion, we were lucky enough realizing that the log transform would probably simplify our stochastic differential equation significantly. It did indeed simplify the stochastic differential equation significantly. And as a result, we managed to solve it and to construct the density as well. In the general case, the only thing we need to do is to solve the Fokker-Planck PDE. Obviously, as we already know, this partial differential equation doesn't define the probability density function by itself. We need to supplement it with the initial condition. What would be the initial condition? At time t equal to 0, the value of our process is equal to S0. So the value is deterministic. A deterministic value means what is the probability density function of a deterministic value? You would say deterministic value is not a random value. It is not a random variable, so it doesn't have a probability density function. Or does it? Any ideas, please? If the value is deterministic, the probability density function is the so-called delta function, Dirac delta function, if you remember it. It is a Dirac delta function. P of s at t equal to 0 equals to delta function of s minus s0. What does it mean? A delta function is a spike, if you remember. So this delta function of s minus s0 is such that it is equal to 0 everywhere apart from this point S0, so this is S, this is S0, and at S equal to S0, this function is equal to plus infinity, so it is 0 everywhere apart from a single point. In that single point, it is equal to plus infinity, and the integral of this delta function from minus infinity to plus infinity, delta of S minus S0 ds, is still equal to 1, as it should be for an integral of the probability density. So we start with a very peculiar initial condition. We start with the initial condition being a spike, a delta function, and then when time increases, we get normal, not a delta function, but our normal, let's say, hopefully continuous probability density function, which is a solution to our Fokker-Planck partial differential equation. The process of our probability density evolution is actually a process of dissipation or diffusion. I will explain in a second what it means. Next screen, if you don't mind. So how it works. Initially, obviously what I'm going to explain now is only a qualitative picture. But this qualitative picture is very much instructive. So okay, this is S, and this is our probability density function P of S at different times t. Initially, at t equal to 0, we have this spike. We have this function which is infinite at t point S0 and 0 outside. Then at some t greater than 0, we have a spike, but a finite one. So we have a function which probably decays outside of S0 and still has a maximum at S0, maybe at some other point. The more time is passing, the less prominent our spike is. So eventually, we'll get a probability density function which is spreading around the initial point with its maximum being less and less and less pronounced. You can, and in all cases, the integral of or under this function for any t will have the integral from minus infinity to plus infinity p of st ds equal to 1 invariantly. So you can think about this as just dissipation of a so-called probability mass. Initially, the whole probability mass is just contained in one point, in point S0. So this spike contains the whole probability mass, and this probability mass is 1. Then this heap of the spike of the probability mass starts to decay. So the probability mass crumbles around, it decays. So basically the probability mass is moving outside of the initial point, and the spike itself becomes less and less and less prominent. Eventually, at t equal to plus infinity, there would be an opposite situation. Originally, we had the whole probability mass being concentrated in the point S0, where S0 is the initial condition. So it was 0 outside of that point and infinity at this point. Eventually, at t equal to plus infinity, we'll have other way around. We'll have our probability density function P of S and T at T equal to plus infinity being 0 everywhere for any S. So the probability mass decays now to spread equally over the S-axis, and it will be 0 everywhere. And yet still, the integral from minus infinity to plus infinity of this function P of S plus infinity ds will still be equal to 1. This integral is 1 for each and every time t. So the Fokker-Planck partial differential equation describes the evolution of the probability mass. Okay, so that's a very important thing. If you can't, if we can't solve this equation, how to solve it actually? We may or may not be able to solve it analytically. So how to solve the Fokker-Planck PDE? Several ways. The first way is analytically if we can. In many cases we can't. A closed form analytical solution typically does not exist. It does exist for stochastic differential equations. Obviously, it does exist for a Brownian motion itself or a Brownian motion with a constant trend. It does exist for Ornstein-Uhlenbeck partial differential equation. It does exist for geometric Brownian motion. It does exist for, although it is quite complex, it does exist for so-called CIR process, Cox-Ingersoll-Ross, for example. If you're interested, you can try to solve it. In this case, mu of S and T is mean reverting. It is kappa times theta minus S, where kappa and theta are constants. And sigma of S and T is some constant, let me say epsilon, square root of S. This is a very well-known model in financial mathematics, typically used in modeling commodity prices and volatilities. In this case, you can obtain the analytical solution as well. In most cases, in most other cases, you can't. So the general way of solving the Fokker-Planck PDE is a numerical solution. And the third way is a method which is, let's say, solve it asymptotically. I will explain what it means. Asymptotically for small t. In this case, you don't obtain the exact closed form solution, but you obtain some kind of approximation. So basically what you need to do is to approximate this function P of st when t is small, and this function P of st is not very much different from the original delta function, from the spike. And that's why those asymptotic solutions, they would take a very specific form, very similar to the Gaussian distribution, with the standard deviation being close to 0. So in general, the method for constructing asymptotic solutions to the Fokker-Planck partial differential equation, there are several methods, but a very well-known method is called the method of heat kernels. I am not going to explain in very detail how it works, but I just want you to be familiar with this term. And if you find it in the literature somewhere, somehow, sometime, for some purpose, you will understand what it is all about. It is an approximation which allows us to provide an approximate formula for our P of ST, for our probability density function, at times close to 0. But what about the numerical solutions? It is a very important, I think, very important technique to understand. Can you tell me, please, so all of you came from different backgrounds, any one of you familiar, we may have discussed that, with numerical methods for solving partial differential equations? Please don't be shy. Numerical methods for partial differential equations. Anyone? No? Okay. I will give you some explanation of how in general this can be done. And I will also send you a reference to a very excellent book which describes this technique in detail. Actually, being able to solve partial differential equations numerically is very important for many areas of applied mathematics. For the probability theory and stochastic process, definitely yes, because we now know that the Fokker-Planck PDE can be solved that way, and very often it is the only way of how we can solve it. But you have already seen other partial differential equations. You have seen the Black-Scholes-Merton PDE. You have seen a very close analog of the Black-Scholes-Merton, which was the Feynman-Katz PDE, you remember? And all of them may or may not have exact or even asymptotic solutions which can be constructed, but it is relatively easy to construct a solution numerically. So how do we do it? In order to construct a numerical solution, we define a grid. In this case, the grid looks relatively simple. Consider a two-dimensional system of coordinates. As you remember, our function P is a function of two variables of S and T, okay? And to that extent, let the horizontal axis be the T axis and the vertical one be the S axis, okay? Obviously, the S axis may extend into the negative as well. Depending on our model, it may or may not have negative values of S. Obviously, if it is a price of some financial asset, then this price cannot be negative, right? But if it is, let's say, an interest rate, then in theory at least, negative interest rates are possible. And nowadays, with all this quantitative easing in place in European countries and in the United States, it may indeed be a good model that, for example, for Swiss franc, for the Japanese yen, and so on, we consider a negative interest rate.
And what is negative interest rate means in this case? I mean, in reality.
It means in reality a very unfortunate reality for you. You have 1 million Swiss francs. You don't want to keep 1 million Swiss francs under your mattress, simply because it is unsafe, right? You don't want to keep them at home. You bring them to the bank. And the bank, instead of paying you a positive interest on your Swiss francs,
they will take fees for that.
They are charging you the fees simply for this nice opportunity to keep your Swiss francs in the bank rather than under your mattress. This is a very, I would say, realistic situation, and indeed the majority of Swiss banks, UBS, Credit Suisse, and so on, they have negative interest rates for Swiss francs at this very moment. Can you imagine that? Unpleasant, but it is a fact. So depending on our stochastic model, the process may be positive or a positive definite or not necessarily positive definite. That's why in general, I construct the grid which may extend in the negative region as well. But because it is a grid, it is bounded. So let's say we have some kind of upper bound for S, which I denote by S max, and I have some lower bound for S, which I denote by S min. Okay? Whereas time cannot be negative. So time starts at 0 and it is only greater than or equal to 0. Okay? Then we construct the grid by considering multiple values of S and multiple values of time. So, for example, consider some point, and this point is surrounded, suppose that now H is our step in S, and let's say tau is our step in time. Okay? And then we have a grid. Okay? So any point here, let's say I will denote this point by SI TJ, where moving by index 1 to SI plus 1, let's say SI plus 1 minus SI equals to step H, and obviously TJ plus 1 minus TJ equals to our step with respect to time tau. What can we do? We can do a very simple thing. Initially, there would be some point S0, the initial point of our process. So S0 is here. Actually, S0 may or may not lie on the grid node. But ideally, you would like to construct the grid in such a way, it is just for numerical stability and other nice properties, that your initial point S0 is directly on the grid. Okay? So it is somewhere here. Your point S0 is directly on the grid. Now, at any time t, for example, tj, we consider the neighboring points to our point si. So this is the next one, si plus 1. This is the point si minus 1. And remember that we have to solve the Fokker-Planck partial differential equation, which in this case I can write in the following way: dp dt equals to minus dds of mu p plus 1/2 second derivative with respect to s of sigma squared times p. What we do, we solve this equation by time forwarding, moving forward in time. Obviously, at time t equal to 0, our solution is known, right? What is our solution? We know that at point S0, the solution is what? Infinity, right? In all other points of our grid, at time t equal to 0, the solution is 0. What we will do, we'll probably do a slightly different thing. And we would say that in this point, in this particular point, where the solution should be infinity, it wouldn't be an infinity. Instead, we would take P in this point, in some point I0, which corresponds to the initial value S0, and T equal to 0, on this grid numerically. Instead of setting it to infinity, we'll set it to 1 divided by h. Obviously, when h, the step with respect to s, is small, then this value is indeed large and will be tending to infinity as h tends to 0. But still, we'll use some kind of small but finite value of h. Anyone can tell me, please, why do we make this strange choice? Why do we put P of I0 and 0 at 1 divided by h? Because then, if we integrate our function P numerically over the grid, again, instead of taking the integral, you remember integral from minus infinity to plus infinity, P of s anytime t ds must be equal to 1. But we have a grid, so we don't take this integral. What the grid will give us, we have some I minimum here, and we have some I maximum here, corresponding to S min and S max, right? And S max. Therefore, this integral is approximated by a discrete sum, I from I min to, let's say, I max minus 1, P evaluated in some point Si and T. What is ds? ds in this case is precisely the step with respect to s, and it must be equal to 1. Therefore, if we indeed define the initial value for our function p in such a way that it is equal to 1 over h at point I0, and it is 0 in all other points, then this condition is satisfied, and we have indeed this numerically evaluated integral over the grid being equal to 1. The total probability mass is equal to 1. It is non-zero in only one point currently, but that is only for t equal to 0. Now, suppose that for some t equal to, let's say, tj, we already have p of si tj for all I and j. And we would like to move to tj plus 1, which is obviously equal to tj plus 2. What do we do? We discretize this partial differential equation. We can do it in two ways. And the first and the most simple way, which I will present to you, it is a so-called explicit discretization scheme. How do we construct the partial derivative dp dt? Very simple. This is looking at our grid. This is tj. This is tj plus 1. So tj is here. What is dp dt? This is simply p of any si at point t j plus 1 minus p of si at point tj divided by the time step, which is tau. We replaced our derivative by a finite difference, right? We used a very simple first-order finite difference approximation for our probability density. This P of Si Tj, it is known. We know that the probability density function is already completely known for all values of t up to Tj in all nodes of S, where this value is unknown. It is to be determined. Okay. What is the right-hand side of our PDE? Very simple. What is the partial derivative of mu p with respect to S? This is simply, now with respect to S, it is mu. You see, we have points Si plus 1 and Si. The best thing we can do is to take a two-sided derivative. So it would be mu of Si plus 1 Tj minus mu, times p of Si plus 1 Tj minus, in a similar way, mu in the point I minus 1 Tj and p in the point I minus 1. I just do not write it completely, but you understand what I mean. Divided by 2 times h. And this is to be taken with the minus sign because there is a minus in front of the corresponding term in the Fokker-Planck. Plus 1/2. Now there is a finite difference approximation of the second derivative. You can very easily see that the second derivative is approximated in a similar way. It is mu in the point I plus 1 and all of them Tj, p in the point I plus 1 minus 2 times mu I pi plus mu I minus 1 p I minus 1, all of them at Tj divided by h squared. So the right-hand side is completely known because our function p is already completely known up to time Tj. And obviously our functions mu and sigma, not mu, sorry, my apologies, sigma squared here, sigma squared here, sigma squared here. And the functions mu and sigma squared are to be evaluated in each and every point. So we can easily compute what sigma squared of S, for example, I plus 1 Tj is. It is just directly computable. So the only quantity which is not known here is precisely our p at Si and the next value Tj plus 1. So what we can do? We can simply solve this equation with respect to this unknown quantity, and that's why when we know the values of our function at Tj, we then obtain the values of our function at Tj plus 1 as well. Very easily. In addition, it is a good idea when solving the Fokker-Planck partial differential equation to set up also the boundary conditions that p would be identically equal to 0 at the lower bound and at the upper bound. Here P is equal to 0 as well. How to specify these bounds, how far they should be from the initial point? The best answer is just to conduct a numerical experiment to do that. This explicit discretization scheme is very, very easy to implement, and I suggest that you play with your favorite numerical software. It could be Python, NumPy, or C++, or MATLAB, or anything that you implement this scheme. It is very, very easy. It is just simple iterative forwarding over time from t equal to 0 to t equal to tau, 2 times tau, and so on, because in general we understand that tj is simply equal to j times tau. And you will see how this probability density function dissipates. There is a disadvantage of this explicit scheme, is that it may be unstable. So you would suddenly see that instead of this nice dissipation, the probability mass decay dissipation, as we have seen in the previous example, you would get some unusual behavior. Either your probability density could become negative, or it could get some strange spikes, and so on and so on. This is a very well-known phenomenon in numerical solution of partial differential equations. If that happens, you need to reduce your time step tau, but you can't reduce it indefinitely. If you make it too small, then your scheme is probably stable, but you still get errors due to too many steps and rounding errors accumulating with them. For that reason, there is another way. We can write our partial derivatives in a different way. So the left-hand side, instead of taking the difference between tj plus 1 and tj, we can write it as a difference p, let's say si, other way around, t. Okay, for the left-hand side, sorry, for the left-hand side it could be the same. It is p of si tj plus 1 minus p of si tj. But the right-hand side, in this case, can be evaluated at j plus 1 rather than j. So you would have p of s whatever tj plus 1, and so on, p of whatever tj plus 1. In this case, you wouldn't be able to determine your p of si and tj plus 1 by just solving one single equation here. You will get a system of linear equations with respect to all those p si tj plus 1. Also taking into account the boundary condition that they are 0 here. So we will get a system of equations with respect to p of si, I from I mean, okay, we know that it is 0 to I max at tj plus 1. You have a system of linear algebraic equations. Still linear and algebraic. From your first year linear algebra, you know that in general the system can be solved. Moreover, in this particular case, the system is sparse. And there are some very efficient techniques as compared to the general case of how to solve this system. And this is a preferred way. In that case, you have a stable procedure. And moreover, you can prove under certain conditions that your probability density function is guaranteed to be non-negative, which is a very good property, obviously. if you know that it is non-negative in general, then you want your numerical scheme to preserve this property. Your probability density may be computed still with some numerical errors due to this discrete approximation and due to rounding. But at least this very important property is well preserved. So I would like to ask you, would you be able to do, I will circulate a book on numerical solution of partial differential equations in finance with you. And we will do, because we do have practical sessions in addition to our lectures. Previously, we were using up our practical sessions time to cover more material extending the lectures. But this time, I would like you to implement a simple solver for Fokker-Planck partial differential equation using one of the methods presented in that book. I have already outlined the general idea of how it is done. I will circulate the text with you and also send you an exercise. In general, because we're on a remote mode now, I would not say that it needs to be done strictly individually and so on. So please feel free to team up with your friends, but still not to make one huge team. And what I would like you to get, let's say, a hands-on experience in solving the Fokker-Planck partial differential equation numerically. Okay? It's probably all today. We have constructed the Fokker-Planck PDE and we understood what it is for and how it can be solved numerically. We'll then do a numerical exercise using your favorite programming language, Python, MATLAB, C++, name it. Okay? Your feedback, please.
Hello.
Hello?
Can you hear me?
Yes, yes, I do.
Could you please write in Telegram or in Moodle the exercise precisely, like what
Yes,
should we do exactly?
Absolutely. Absolutely. Telegram is actually easy for this type of communication, so I'll circulate it over the Telegram. Okay?
Okay, thank you.
Okay. Any other questions, please?
Sorry, what about the grades of the midterm?
Okay, I will discuss, good point. I will discuss them next time. We'll begin with that. Or
Okay,
I can circulate them before and my comments before our lecture next time, and we will have an opportunity to ask questions. Okay?
Okay.
Okay, then we're done for today. Thank you very much for your attention, and we'll continue in a similar way next time. I will make login to this session easier. And again, circulate the book and this program assignment for you. Okay. Thank you.
Thank you.
Thanks.